Hi, Harvey here from the Coherence team. Today I'm going to speak to you about a new feature we've added in 12.1.3 called Asynchronous Entry Processors, and I think the majority of you can gather from the name pretty accurately what this feature is. Entry processors, we're going to have a very brief introduction onto entry processors for those of you that are unaware. I assume that most of you are aware, so I'm preaching to the converted, but we'll just set the scene a little bit and then talk a little bit about why the contract today is synchronous and how you may want that to be asynchronous. You may not require such a rigid contract. And then we'll talk a little bit about why converting a synchronous process to an asynchronous process, using the obvious approach may not be something that is most effective, or how we can actually add features onto the asynchronous entry processor that make it unique. And obviously then we'll go into an introduction of the asynchronous entry processor, but I want to kind of get through these slides pretty quickly so that we can get straight into an IDE and start looking at what this is and looking at the API and writing some tests and exploring each of those behavioral differences that you can specify as parameters. So let's get straight into it. So entry processors themselves, so generally clients, they can do a get of a key. So this is a distributed hash map. So we get on a key, returns a value. We may want to mutate the value and put the key back. Now on a distributed hash map, that means that the get itself is going to be a remote call, the put's going to be a remote call. And so it's very expensive, let alone if you wanted a pessimistic locking strategy and you wanted to lock it to ensure you had exclusive access. So to avoid that, we introduced the notion of entry processors a very long time ago. And the actual invocation mechanism is that you can specify an entry processor on a specific key, a collection of keys, or a filter, kind of similar to a JDK predicate. And we'll go through a couple of those scenarios in the next few slides. But the other thing that it's allowed us to do is provide features on top of it. So you may want to, we introduced something called partition-like transactions, and there is another screencast on this, so I recommend you have a look at that if you're interested. But the notion is to be able to mutate other entries that are co-located to the entry that you're requesting the entry processor against. So you say entry processor against this particular key, and it may be that you also want key 1, 2, and 3 that are also on the same partition as key. And if they are, then you can enlist those entries, mutate them, and have that operation committed as an atomic unit of work. Okay, and that's what we call partition-like transactions. So moving on, let's have a look at the high level what this looks like. So here we have a client and we have a storage member 1 and storage member 2. For the purposes of this asynchronous entry processor talk, what we're actually focused on really is the client and how the client is blocked throughout this entire operation. But if we kind of break down the actual entire operation, we have a name cache invoke, which is the key in the entry processor, which gets sent to the storage node. The storage node will then deserialize the entry processor and call process on the entry processor. And entry processors can return a value as well. When we call the process, the entry processor may mutate the value, might change value v1 to v2, which will incur a backup. So the backup gets sent, and then we send the response back. Now, throughout this whole interaction between the storage node, the backup, and initiated from the client, everything from the Coherence side is asynchronous. All the messaging layers within Coherence are asynchronous. So when we send a message on the wire, and kind of the request from the originator is sort of complete, so i.e. from the storage node needs to send the backup request. When it serializes the backup message and puts it on the wire. As soon as it's done that, and it kind of completes all its finally blocks, then it's free. That thread is free up to do some other processing, and only when we hear back from the backup do we actually then go off and post back to the client. Right, so all of that is all asynchronous. But from the client's perspective, they did a name cache invoke, and the contract states that we need to return from that name cache invoke with the result of the entry processor. So we have to hold on to the client thread. We don't return control to the client until we receive the actual response, and at that point we can respond back. And if we look at the other two variants, so this is the collection of keys, it's all very similar. I mean, we also have a third storage member here, but the third storage member never received the original invoke request from the client. As you can see here, the collection of keys was a collection of keys that was owned by two members, not the third member. So the request goes to 1 and 2, and the backups for the keys that are owned by 1 and 2 may land on 3, so it may have some work to do, but it's always instigated by the storage nodes in this case. And the important part here is if we look at the client, again the client sends the invoke, we don't return control, but now we have partial responses coming back from 1 and 2, and only when we receive the full response will we return control back to the client. And again, if we look at the filter approach, now the filter has to go to all storage nodes because the filter is a predicate that is executed on all the keys that are owned by that storage member, such that those keys can be reduced to a subset, and the entry processor is executed on the subset. And again, that's a potential reduction. It may be that you have a filter such as a always filter, which always returns true, so every entry complies, and we'll call entry processor on all of the entries owned by that storage node. And again, if we look at the client side, we're getting all of those partial responses, but this time we have to get the response from 3 as well, before we receive a complete response. And once we receive the complete response, we can return control to the client thread. And this may not be something that you want. You may actually want to be able to be asynchronous. You may have a pipeline like that is illustrated here that you can kind of break down. If we look at the right-hand side of this diagram, we can see that we basically need 3 threads. As soon as we have 3 threads, we can halve the time of this entire execution. Okay, and so we can see that A and B we can kick off in parallel. The entry processor and C are dependent on B, but once B completes, we can kick off the entry processor and C in parallel, and D is dependent on the result of the entry processor. Okay, and so the answer might be simple. Many of you in pre-12.1.3 may have come across this exact same requirement and thought, well, we'll just kick off a thread. Kick off the thread that does the invoke, and it's done in parallel, it's another thread. But the problem is that you're kind of burning another thread unnecessarily, because as soon as you do the cache invoke, we serialize what we need to in terms of the request message, put it on the wire. But as soon as we put it on the wire, the thread's kind of parked and it's not really going to be doing anything. So it's unnecessary waste of resources. The other thing is, what if you wanted multiple invoke operations? So imagine within this run method we had invoke 1, invoke 2, invoke 3. Now if you look at how you would do this in this thread, and obviously 2 is dependent on 1 and 3 is dependent on 2, but if you would do this in this thread, when you do the invoke operation, it goes across to the storage node, and only when it responds from the storage node and comes back to the client do you then do the invoke on 2. Now wouldn't it be nice to be able to say invoke 1, invoke 2, invoke 3, and they all land on the storage node, and the order in which they were requested by the client is preserved, such that when the storage node actually comes to executing these requests, it will execute them in the order of 1, 2, and 3, regardless of if a partition moved or there was any kind of systematic issues that happened in the cluster. Okay. And so that kind of leads us quite nicely onto asynchronous entry processors. So it's a new feature introduced in 12.1.3, and it's actually a wrapper entry processor. So asynchronous processor is an entry processor implementation. It's kind of a marker. It tells the API effectively that this is an entry processor that can be executed asynchronously, which means that the contract of invoke can be loosened. So we can say we can return pretty much immediately as soon as we build the data structure, send the message out, and are able to do that. Once we can do that, we will return, and that's all that needs to be done. The asynchronous processor itself takes the entry processor that needs to be submitted. So it's kind of a wrapper processor. And asynchronous processor itself is a future. And that's because it extends from asynchronous agent. And so what that means is that from a client's perspective, once you submit the asynchronous processor and you go off and do some extra work, you can actually call get on the asynchronous processor, and it will block the current thread until the response is received. And as well as that, we can change the behavior on the asynchronous processor in a couple of ways. One way is the unit of order. So we mentioned in the previous slide about this invoking 1, 2, and 3. So what preserves that order on the storage side is something called unit of order, and by default we use the current thread's ID. And so when we kicked off that new thread to do the invoke 1, 2, and 3, we ensure that order is maintained because it's the same thread that's doing the submission of those requests. Now, you can specialize that unit of order. So you may want to say that I want a unit of order that spans threads, or a unit of order that is for a certain number of operations within the same thread. So it's not global against the entire thread, but certain operations should maintain the order. Okay. The other thing that we've added is something called automatic flow control. And flow control is a means to stop a client bombarding a storage node. And so, as you can imagine, that there may be a sort of relentlessly request executing client, right? So a client may submit multiple invoke operations in a tight loop, which cause all these requests to be sent out to the storage node. But the storage node may become sort of overwhelmed with all these requests that need to execute, and its backlog may grow exponentially, right? So based on the number of clients and all of those being in a tight loop, submitting these requests. So we introduced this notion of flow control, which we'll go through an actual example and test this and show this to you. But the idea is that we want to preserve the storage node's ability to respond to these requests. So from the client side, if the client is, like I say, relentlessly submitting these invoke requests, we kind of determine that the member that's actually responsible for executing these requests becomes clogged, we start to pause the client until we become unclogged on the storage side. And you have the option to kind of turn this off if you want. But we do want to remove the possibility of having a sort of denial of service in the storage nodes. Okay, so let's get into a demo. Okay, let's get rid of PowerPoint and switch to the IDE. So I've got two things here. I have my IDE on my right-hand side and I have Emacs on my left-hand side. Let's focus in on the IDE. We won't be using Emacs very much, to be honest. Emacs has my terminal and a couple of log windows. We'll be using that for the final test just to verify some output, but let's look at the IDE. So I have a project called Asynchronous Processors. It has a sleep processor and a cache configuration file. Cache configuration file is very simple. All caches go to this distributed scheme, and it has a thread count of 5. That's the only real important parts. The sleep processor itself is trivial. It sleeps for the prescribed amount of time. It also logs how long it's sleeping for on which key the process is also called for. And as well as that, once it completes its sleep, it always calls the pass-in processor if one is provided. Okay, pretty simple. So let's start by creating a test. So in here, let's just create an asynchronous processor tests. Okay, and we'll just remove this sidebar to give us a bit more room. So let's start by creating a test. And we're going to just call this test AP. Okay, pretty simple. So first of all, to start everything off, I kind of need a cache. So let's use a well-known name in computer science that is completely overused, and we're going to call this cache. Okay. And so we have a foo cache, and the first thing we're going to do is we're going to just put a value in there, something that we can work against. The next thing we're going to do is we're going to start creating our asynchronous processor. So we have this processor, and for that we're going to create a new asynchronous processor. And as we said through the slides, it accepts 3 parameters. So the entry processor that will actually get passed to the storage node, whether to enable flow control or not, and the actual unit of order for this asynchronous processor and subsequent asynchronous processors. So let's start with doing an out-of-the-box entry processor called number incrementer. A number incrementer itself takes a value manipulator. Now, a null value manipulator suggests that I want to actually update the entire value itself. So I'm going to say I know that the entire value is an integer, and I'm going to update it by 10, and I want it to be a pre-increment. Okay, so that makes post-increment false. Oh, sorry. that's better. The next thing I'm going to do is I'm actually going to submit this request. So against 0, execute this processor. Okay. Now it'd be great if I could kind of verify that while this processor is executing, I can do something concurrently, and this thread can invoke it and see the result of that concurrent to the actual invoke operation. Just to kind of reify to ourselves that this thread is not blocked. Okay, so let's do that by just doing a query. Okay, now we know that queries won't actually acquire any locks on the storage side. Okay, so it means that we can execute this query concurrent to the processor, which we know will have a lock on 0. Okay, so if this was cache.get on 0, this would end up being blocked anyway. So we don't want to do that. And then the next thing we want to do is we kind of want to use the future capabilities, the future implementation capabilities of asynchronous processors. So now that we've kind of done some work, which is to actually do this query, we're now dependent on the result of the asynchronous processor. So let's block this thread indefinitely until we receive the response or errors, and then let's just output again. So from this query, what I'd expect to see is 0, 0. From this query, I'd expect to see 0, 10. Now the problem is that because this is a single client, this operation is actually going to be executed very quickly. So we need to introduce an artificial delay, and in comes our sleep processor. So let's sleep for a few seconds, and once we finish sleeping, then we'll do the number increment. Okay, which will allow us to kind of observe that this thread is not blocked while doing this invocation. So let's go off and run this test AP, and as we can see from this output, first of all, we have a distributed cache and we have a worker. So before, when we looked at the cache configuration, you noticed that we had a thread count of 5. So we have 5 worker threads in the pool for this service, which is the distributed cache. So this is the first worker, which is the one that was decided to that was going to execute this entry processor. And we're making it sleep for 3 seconds on key 0. Now if we look at from the client thread's perspective, what it does, it sees 0, 0 from this entry set call, and then it sees 0, 10. So it's exactly as we would expect, and it kind of highlights, first of all, the use of asynchronous processor to execute an entry processor that you want to execute on the storage side, and second of all, the fact that we have this future that we can block the current thread to get the actual response. And if we wanted to, we could specify like the standard sort of asynchronous. We could provide the standard sort of future mechanisms to kind of wait for only a certain amount of time. Now, what I want to show you also, though, is another way to execute or another way to receive the result, without using the capabilities in future. So let's provide a specialization on this asynchronous processor, and it's going to be an anonymous class, which is a subclass of asynchronous processor, and that's so that we can override a couple of methods. Now there are 3 that are of interest here. Now, that is on result, on completion, on complete, and on exception. So on exception is called when an exception is received in executing that entry processor. On complete is executed when all of the results have been gathered and this asynchronous processor has fully completed. On result is for each entry that we receive from the storage side. So if we were executing on a collection of keys or with a filter, we would receive many on result calls for either each key in the collection of keys or for each key that complied with the filter or the predicate, whichever term you prefer. Okay, so I'm going to override this behavior, and I'm just going to get rid of these unnecessary annotations just to make it a little bit clearer. So on result gets called for every entry, and I kind of want to be able to access this entry outside of the scope of this anonymous class. So let's just do a little bit of workaround in terms of providing access to the enclosing class by just creating an entry array and exposing this entry at index 0. So we know that we're only ever going to have one entry, so we can do this very easily. And that means that outside the anonymous class, let me just remove this to show us the screen a bit easier, we can now access the entry. Now, we may want to go and do some work, and while we're doing that work, we might want to check back to see if we've actually received the entry. Okay. So only while it's null, go off and basically, do some work. The other thing that would be nice to do is if I synchronized on this particular instance, I'm gonna, this is me again artificially sort of doing some work. So every half a second, and let's make it clear that we're doing this, spinning for half a second. So this kind of simulates the fact that we're going to go and do some work for half a second, and then after half a second is complete, we'll come back to this loop and we'll check whether this entry is equal to null. And it kind of also be nice to be able to say, to kind of short circuit this as well. So in the case of having the result and the entry processor complete by the time or before, while the other thread is still in wait, it'd be nice to short circuit it and notify it that the completion has happened. So let's do that by synchronizing on the monitor, the same monitor that's used by the enclosing class, and notifying a waiting thread. Okay. So if we, before we go any further, let's just correct a bug that I just noticed. So we want to make sure we notify the same thing we're synchronized on and the same thing that is being, and the same monitor that's being waited upon. So bug avoided. So let's run this test AP. And what we should see is similar to what we did before, we should see 0, 0 execute here. We should see this about 6 times as we're sleeping for half a second, and as we're waiting for half a second and sleeping for 3 seconds. And again, we should see 1, 10 as the result. And if we look down here, we see 0, 0, we see this output 6 times, and we see 0, 10. So just as we expect. The other example I wanted to show you was the unit of order example. And I think this one's useful to see, but I want to spare you from me typing this over and over again. So let me just paste in a test that I built before in true Blue Peter fashion. Here's one I prepared earlier. So here we have a test unit of order, which again we're using cache foo, cache.put 0, 0 to prime the value. Now I've got a calculation that I'm going to perform. I'm going to plus 10 and times 100. Now, if this calculation is performed out of order, I can get different results, as you'd expect, right? So basically, if I execute 10, so we start with 0, execute 10 plus 10, 20 times 100 is going to give me 2,000. If I executed 10 times 100 to give me 1,000 plus 10, I get 1,010. If I execute 100 times 0, I get 0 plus 10 gives me 20, right? So I can get these different permutations if they're executed out of order. So I'm going to run this, which basically invokes each of the asynchronous processors. And the important bit is, so we invoke the asynchronous processors, we wait for all the results, and if we ever see something that's unexpected, we observe it by this failed calculation message. And you can see here that we didn't see that message. Now, rather than a constant unit of order, which, by the way, we would have had by default, considering we're using the same thread, so it'd be the same thread ID, but I just wanted to make it very explicit by a constant. Now let's use a random unit of order ID and see if we ever fail the calculation. Now don't forget, we're going to have many worker threads. It's going to be submitted to each worker thread, so each worker thread can execute this in parallel. And because we're executing on the same key, they're all going to contend on that key. So we got 3 requests that we're submitting. Each 3 requests is going to be served by a different thread. As soon as they try and acquire the lock, it becomes undeterministic on which one will actually receive that lock first. And you can see that we failed the calculation 5 times. Now I've seen this fail 10 times, 15 times, 1 time. it's a single storage and client node, so that does have some bearing on it as well, but it's completely indeterministic on the order in which this can happen. So the unit of order allows you to, for a single thread, everything gets executed in order by default anyway, but it'll allow you to say, for multiple threads, I want a global unit of order, or it'll allow you to say, for a single thread, I can partition bits of the work that's being done for that thread asynchronously with different units of order. So I might have everything operating on 0 on the same key within a thread has the same unit of order. So 0 has this unit of order of n, and 1 has a unit of order of m. So they all get grouped together, right? So that's unit of order. There was one other part that I really wanted to go through, which was this notion of flow control. And I kind of wanted to explain that. And this one's a little bit more of a in-depth test. And so I will explain the test, and we can see it work. And I kind of want to run this one against more than one storage node as well, just to illustrate the test. So I've called it test clog, and the idea is that we have this flow control to stop a client that's in a tight loop submitting asynchronous requests, bombarding the storage node and causing this kind of backlog to increase. So the way I've done this, so by default the clog count is 1024, and the way I've done that is I'm going to submit all of these requests to each member. So I want a request. So I want a thread on the client side, a thread to execute n number of requests, and n is going to be clog count -1. So 1023 requests I want to be submitted to one storage node, and then as soon as I get to that 1024, which I know I'm going to kind of become clogged, at that point, just before that, I want to output a message, and then I want to submit that that next request that kind of tips me over the edge, and I then want to output a message once this thread becomes unblocked. Right, so we block that thread because it's kind of in a tight loop, submitting these requests, and the storage node can't keep up with the requests that the client is submitting. And so that 1024th request will become blocked, and what we should see between the two messages is we should see about a delay for about 5 seconds. And the reason is because if you look at this logic, we actually we saturate the thread pool. So we know we have a thread pool of 5. So the first 5 requests that we submit, which are going to be on different keys, cause each of those threads to sleep for 5 seconds. And then after that, we just submit another 1018 requests to cause us to get to the clog state, right? To get us to kind of cause the flow control to become active. Okay, and I mean you can have a look at the details of this test, but basically to ensure that all the requests go to a single member, we pick a single partition for that member, and we use a composite key where the first part of the composite is a partition-aware key, and that will guarantee that it will land on that partition and therefore that member. But as well as that, we then have a unique integer for each request. Okay, so this is a composite key. Okay, so sounds pretty simple. And then the other thing we do also is we execute all of these in parallel. So we just have this method factored out, which creates a thread pool for each member, effectively, each storage-enabled member, and we do an invoke call on them and await their termination. The other thing we want to do is, I think it'd be useful to make this test storage disabled. Okay, so to do that, we'll just add a before class annotation, so we know that this system property is set. And as we're going to make that storage disabled, we better start a couple of storage nodes. Okay, so let's start a couple of storage nodes. The only thing I'm specifying, so this is going to kick off 2 default cache server instances, this script, and it's going to, as the class path, as well as coherence jar, it's going to have the asynchronous processor demo jar as well, and we only need that for the sleep processor. So let's have a look at the actual logs. Here's one, and I'm just going to auto revert so that we see the changes as they happen. So it turns into basically into tail mode, and again the same on this. There we go. Okay, so the next thing we'll do is we'll run this test clog example, and what we should see is each of the threads on the storage node end up having this sleep execute, and we should see 5 seconds between the expecting this next request to clog and the clog. So we can see, if we look here, we can see that this thread here, which is the 0 worker, sleeps for 5 seconds. We see 4 sleeps for 5 seconds, 1 sleeps for 5 seconds, 3 sleeps for 5 seconds, and 2 sleeps for 5 seconds. So we have 5 threads that are now sleeping for 5 seconds. And that allows the rest of this callable to then submit another 1018 requests to cause that clogging, right? And enact the flow control. So we can see here, pull 1, thread 1, is expecting this member 1, and we're submitting it on partition 231 to become clogged, and therefore pause this thread. Okay, so that's pull 1, thread 1. And we can see pull 1, thread 1 is also the second to last message that we receive, where the client thread becomes unblocked. So I wonder what the time difference between those two log statements are. And if we have a look, it's exactly 5 seconds. Okay, well, okay, 5 seconds, and it took us just under 200 millis to execute the other 1018 requests across 5 threads per member. Okay, on this single client thread. Oh, sorry, on this single client JVM. So that's kind of illustrated to you the fact that the thread can become paused if the backlog increases too much. And again, that can be disabled through specifying the flow control as false. Okay. So let's get back to the slides briefly. So again, thank you very much for watching this screencast, and I hope it's been useful for you. You can contact us through various mechanisms such as Twitter, Facebook. We have an RSS feed. We have a LinkedIn Coherence user group. You know, hopefully you found the YouTube channel. Otherwise, I'm not sure how you're watching this video. And we also have special interest groups that we have around the world. So where many people speak, from engineering to coherence evangelists, and we encourage you to come along if you're in the area or have the time. Thank you for listening.